So my name is Anna Baotić. I'm currently working as a project manager / business analyst at a company called APKs in Croatia. So we are here at the bottom of Europe. We have a lovely, lovely coast, and this is the location where Game of Thrones is being filmed. So if you like that, you should visit, but not any time between January and November because it's impossible to get to the city due to all the people. So we will be discussing certificates and keystores today on Android. So before we actually begin, I would just like a show of hands who here does Android. Okay, and the rest of you are developers. A few. Any management here? To manage. Okay. Okay, so to cover this topic, which is obviously very, very interesting, and people love dealing with certificates and keystores, especially when they have an issue with them. Until then, it's all good and fine, but when issues start rising, then all hell kind of breaks loose. So let's first define what a certificate is. Simply said, any kind of certificate is an electronic document that proves ownership of a public key. Straightforward, simple, no need to kind of elaborate on that. That document is used in TLS, or transport layer security, meaning that each time any kind of server communicates with another or a client, they exchange data proving basically who they're talking to. Now, it's also used in electronic signatures. We'll get to that a little while later. Basically, you do not need a pen and paper to prove something or to sign something or to say, okay, I will take this loan and here's my signature. You don't need actually to go to the bank and use that pen to do that. And finally, certificates have a specific structure which contains information about the owner or the issuer, or basically what kind of public key information is in that document and what kind of fingerprints it has, because those are very, very important. Now, I already mentioned that every certificate kind of includes information about an identity of its owner. Now, that means that you can place information about your name, your address, your company's name, where it's located, basic information that says who you are into that certificate. And I also said that it proves ownership of a private key, of a public key, excuse me. Since we have a public key, it kind of insinuates that there is maybe a private one. Now, we just need to digress a little here. So has anybody done anything with asymmetric cryptography here? Okay, so half hands go up. So asymmetric or public key cryptography, for those who don't know, is basically any kind of, system that uses pairs of keys that are not symmetrical, so they are not the same. And any kind of infrastructure or PKI is just a set of roles, policies, and rules on how to store and manage the keys that you have. Now, if you create a public key or a private key, it needs to be created in an economical manner, meaning that if you need a set of keys, you must be able to generate them, let's say, in a few seconds. So the operation, although very complex, needs to be fast as possible. And you do that by having, based on a private key that you have, you do some black magic there with algorithms that are at your disposal, and you get the public key. And the idea is that if you want to reverse something or determine a private key based on the public key, you're not able to do that because you don't have all the time and all the resources in the world or the computing power that's able to basically backtrack the whole process. Now, regarding those keys, one is private, the other one is public. That is simple. The private one truly belongs exclusively to the owner, and we will be addressing this throughout this whole presentation. When I say only the owner, it has to be secure and private and really not be accessible to anybody anywhere. The public one is obviously shared among all the entities that need to have it. The private one is used to decrypt messages and the public one to encrypt them, meaning that if I want to say something to the server, I encrypt it with my public key, send it, and the server can use that a private key to decrypt that message. And only he or it will be able to decrypt it because nobody else has that private key. Also, keys are used to calculate signatures and confirm them. Now, it is usually the private key, it's always the private key that calculates any kind of signature and signs it, and then anybody with the public key can say, okay, that's correct, that can be verified. And basically, digital signatures are very, very important today. Like I said, it's kind of a mathematical scheme that is used to demonstrate authenticity of something, and we are using it every single day. For instance, you use it in terms of authentication, and that means you need to be able to determine who you are. So if I say that any kind of digital signature is created, basically we need to know who created it, its identity. We need to be sure there. It's also used for no repudiation, meaning that we know who sent it. Now there's an asterisk over there saying that, okay, you either sent something and we know who you are, or if you say that you didn't send it, it means that your key is no longer private and no longer belongs to you. Somebody stole it. So we are sure that the message either belongs to somebody or that the system has been compromised. So that's very, very important. And finally, integrity, meaning that whenever you send something, any kind of message, document, API response, bringing back your balance from your bank account, you need to be sure that that content was not modified somewhere in the channel. So you need to be sure that the information that you finally get is actually the verified one. So how do we create any kind of digital signature? Well, first you calculate a hash or a digest of a message. It can be used, any kind of algorithm can be used to get it. You usually have a list of which ones are kind of more complex and better and which ones aren't, and it's updated throughout the time. But once you calculate that hash or digest, the sender, so the one who sends the message, will use the private key to encrypt it. Meaning, okay, I will make something with that hash and digest and I will send it onward encrypted. And all those who have the public key will be able to decrypt it and check whether or not that signature is correct or not. Now, after we've kind of climbed up from this rabbit hole of definitions, let's go back to our certificate. Now we said we have the identity and the public key as parts of the certificate, but we also need somebody to say that the whole thing is okay. And that's where certificate authorities come into place. So a certificate authority is any kind of trusted entity, which we say that we trust, that issues digital certificates. Now, it might seem that we're running around in loops here, and we sort of are, because we have this kind of entity who we say we trust that issues certificates and signs other things, but they are not, validated by anybody in terms of entities. There are specific programs or certificate authority memberships that say, okay, for you to become a certificate authority, so somebody who knows what they're doing, you need to prove certain things. You need to jump through hoops. You need to satisfy certain criteria, and that criteria is quite extensive. So once you satisfy all those criteria, you become the entity that is able to issue certificates. Now, the first thing that any certificate authority will do is issue their own self-signed certificate. So basically they're saying, okay, I'm the entity who can say that anything is, any kind of certificate is correct, and the first thing that I will do is create my own and say that it's correct. Now, it is the contract that we say that we trust them, and that's the only basis on this whole scheme. If that weren't true, the whole thing would fall apart. So, the certificate authority will create their own self-signed certificate, and in all your browsers and operational systems, there are those information who is trusted and who isn't. For instance, every time you get a security update on your Android phone or your iOS phone or Mozilla or any other browser, it probably contains some information on which root certificates have been added and which have been removed. So if somebody has been compromised, you want your users to know that all the certificates issued by that authority are no longer trusted. So that's when you get that red notice, get me back to safety, etc., because it's important. That trust has been broken, and you need to be aware that your users might be in danger. So there are several certificate authorities out there. So if you want certificates for your domain or for your company, you will go to the commercial ones and you'll pay a lot of cash, which is an option. Or you will use, let's Encrypt, because that one is free. Now I have had some mixed feedback about Let's Encrypt by people who have been using it in terms of there are no issues, this is super simple, and oh my god, this was the worst experience in my life. So I guess you're either lucky or not, but if you don't want to cash out for a certificate, that's one way to go. Especially if you have a pet project, you might need to pay thousands and thousands of euros or dollars to get that seal of approval. Okay, so what does any kind of certificate actually look like? If you have ever clicked on that little locket in the browser, you will see a certificate, or in this case, in every case, free certificates out there listed. So basically click on the little green locket and show certificate. It will present something like this. Now, if we take a look at the first one that's selected, and that's the bottom of the three, you can, I'm not sure if you can read it or not, but basically it says google.com, and it was issued by Google Internet Authority G2. So Google is getting in the business of certificate authorities, which is fine. And it basically says, details from the subject or the owner, issuer name, it's Google Internet Authority, and it shows more information below for the public key info and the fingerprints for that certificate, but we won't go into that detail. Now, if we hop back once upwards to the Google Internet Authority G2, we see that this certificate was issued by GeoTrust. Okay, and this is intermediate certificate, meaning it's between the leaf one and the first one in the chain. Again, you have the same info, who is the subject, who's the issuer, and again, the info for the public key information and the fingerprints. And if we hop back to the top one, where it says GeoTrust, here we see that this is a root certificate authority, meaning that there's nothing above it. GeoTrust is the one that can say, okay, this is valid, this isn't valid, and they are the one that issued the certificate for the intermediate one. You get some information here about the not valid before, not valid after. Basically, there is a time span in which any certificate is valid. Now, if we abstract this, we basically get a chain of certificates each time we see them. We have the root certificate that uses its public key to verify the signature of the intermediate one, and the same goes back to the leaf one. Now, not all certificates are created equal, of course. So you've probably seen the difference on websites where you have just the green locket and you have the whole full name of the entity that you're seeing. The place where you see the full name, it's called an extended it's an extended validation for entities, meaning they had to jump through more hoops to prove who they are. So in terms of structure and everything else, the certificates are the same, but you had to do more checkups to get the extended validation one. No, this seems like an okay system, but it has its flaws, like everything else. So I like the question basically posed in terms of certificates and HTTPS. So are we safe if we have all this? And there's nothing better than a good sarcastic tweet, and this is one of my favorites. Basically, you can read for yourselves, but it doesn't mean trust this. It means that the connection is private. And again, you might be kind of sure who you're talking to, but not completely, ever. So that's it's an oldie but a goodie, literally. So what is the problem with the whole system? The problem is subversion, or to put it otherwise, overthrowing. your keys can be stolen. Now, by stolen, we might not even say stolen, they might be given away. Now, those certificate authorities that we trust, they're humans behind the whole process. And you know how sometimes you expect the best, best intentions, and you assume stuff? Well, those assumptions can kind of lead in the wrong direction. In 2001, I believe, VeriSign issued 2 certificates to Microsoft, and they issued it in a way that a user was able to open an email address like admin at Microsoft or root at Microsoft, and the certificate authority assumed only a privileged user or an owner can have that kind of an address. Turns out they were wrong, and they sent sensitive data to that email address, and then all hell broke loose. Komodo and DigiNotar had a snafu in 2011, and I think it was TrustWave in 2012 that had some kind of man-in-the-middle issue by by using their root certificates for transparent traffic. So who here knows what a man-in-the-middle attack is? Okay, most hands are up. For those who don't, basically it's when you're communicating with something, but in that channel between you and the endpoint, there's another entity who kind of receives your data and sends modified data onward and backward. Okay, so the scheme is flawed because anything with people in it is prone to errors. We know that, it's common. We just need to work on it to make it safer. And the other thing regarding keys, when they're obviously handed out to people, is how you store them. Now, what's typical for big companies? I mean, not your pet project, not your small startup, Google, Facebook, banks, and systems that really need to be secure as much as possible. They store their keys in something that's called a hardware security module. So I've seen those, we have them in my company, and they're like these weird boxes that have 7 or 10 or 11 slots for physical tokens, and you cannot look at that box from fear of it resetting everything. So if you nudge it, if you kind of drop it, if you raise it, if you change the temperature, if there's humidity in the room, if there's light in the room, if the plants aren't perfectly aligned, that box will say, oh shit, I'm under attack, I need to reset everything. So that's a problem. So basically, if you ever seen those spy movies when there are 2 people, at 3 ends of the room, and they're kind of waiting for that split second to turn something, that's how much careful access is required when dealing with these boxes. And that's where you store the keys. And you typically store them offline, because if they're online, if they're accessible, if you don't kind of need to verify yourself and do separate steps, you can get to them. And if you can get to them, somebody else can get to them. So let's take a look at Android right now. So Android will typically keep you safe as possible, in terms of when it opens a website that has a self-signed certificate, it will say nope. So it doesn't trust you. It doesn't know who this certificate authority is. Any one of you can create a certificate and say, okay, I will be a certificate authority, but your Android phone will say, no, I don't trust you because your root certificate is not installed on the phone. Now, you might think that you can install it there and everything will be fine, and it was fine until Google said, okay, let's take care of this. Again, little mistake, and with Android N, it no longer became possible to install a certificate on the phone and trust. So, we'll get to that a little bit later. If there is something wrong with the chain of certificates on an endpoint, Android will again say, nope. It needs the whole chain to be there, and it needs to be correctly configured before it lets you basically establish the communication. Has anybody here ever pinned certificates in their Android applications? Okay, this is going to be fun later. Okay, so let's talk about signing Android applications. We already said that we can sign anything. We create a hash, I digest, we sign it with a certificate, and everything is fine. So for you to publish any application on Google Play, you need to sign that application. And the process is very straightforward. You generate any kind of key in Keystore, you sign your application, and that's it. You submit it to the Google Play. Now, This process, you've probably been through it, so just show of hands, who here has gone through the whole process and published an application directly on Google Play? Okay, some of you. For those who haven't, if you're starting from scratch, you need to create a Keystore. The UI guides you through it. It's really straightforward. You need to fill in your data, your company's data, and you need to state any kind of password, a secure one, of course. And you need to say how long the validity of that certificate will be. So typically it's 25 years, but with the newest updates, it's possible to prolong that period. Now, if you have your Keystore already set up, you just need to sign your APK. And again, the UI will guide you through it. You just need to select the key that you want to use. But if this kind of Android Studio is too hipster for you, you can always go old school and use the tools that you have, like command line tools. You have your key tool to generate a key. If you ever registered, on the Google Play Developer Console, the key for Google Maps, or let's say Firebase or something, you have had contact with this. You have your zip-align tool to align those APKs, and you have the jar signer to sign it once it's aligned. So either way it goes, it's your choice on how to proceed. But there is one crucial decision here that you need to make, and it's the biggest decision regarding this whole process. And that is who is responsible for your signing key. Now, I will assume that none of you have those security models at home just lying around in a secure room with climate, temperature, monitoring, etc. So I will also assume that at least one of you sometime throughout your career place the Keystore and those keys on Git in the project that they were defined. I will not ask for a show of hands because I would be the first one to raise it. So we were responsible for this at some point in time, especially in the beginning, which is fine because your only expectation is that once you develop a new feature, you will be able to push your new APK to Google Play and just forward it to your users. So the expectation is, again, straightforward. Prerequisites for that to be satisfied is that your signing key is safe and that it is accessible. Now, again, we have two kind of requisites that go against each other. And the way to envision it is like a castle and a moat, where once you have an entrance to the data and you can get to the data, again, somebody else can get to it. So we're trying to be able to get to something, and yet we need to prevent everybody else from getting to it. Now, the reality is that people spill coffee or tea or whatever they're drinking in the morning, and eventually they switch companies. It's not expected from you to work at the same company for 10 or 15 years. Now's the time for me to share a traumatic experience, because most conferences are based on people having traumatizing experiences in their life and they want to help others not live through them. So here's mine. A long time ago, in a country at the south of Europe, there was this developer called John, and John was working on a feature on an application. He finished it from start to end. He pushed it on Google Play, and everybody was happy, including the client. And eventually, he had a problem one morning. He spilled coffee on his MacBook, and a few months later, unrelated to the incident with the coffee, he left the company. Now, a few months later, again, here comes the client and said, I was so pleased with your work, I want to add another feature to the application. And again, somebody took over, developed the feature. UAT was done, the client was pleased, let's go to Google Play again. And at that point, the company had a problem. And the problem was that there was no Keystore anywhere. Nowhere. It was referenced. We could see the data being referenced in Bill Gradle, and we went through Git and saw when any kind of Keystore was mentioned, but it physically was not there. And upon looking at Bill Gradle, we actually realized that that Keystore was nowhere near where it should have been, which is a problem because no more developer, no more MacBook, and you need to tell your client, sorry, we had a snafu and your application will never, ever, ever be updated again. Well, this story has a happy ending because we managed to get in touch with this developer, and that MacBook was actually in storage. Nobody threw it away, so after contacting AppleCare, we were able to get to the data we needed. So yay, happy ending, but this happens to big companies. Not little startups, not your pet projects. It happens to big players, and it's a real problem. It's a big enough problem that Google said, okay, let's help out our developers. And they introduced something that's called Google Play App Signing, which basically says, okay, hand over your keys to us. We will keep them safe, probably in those hardware security modules, and you just go about your business. And the process is straightforward. We won't go into details because it's really explained well on the Google website. So you basically create an upload key for new applications. So you won't be creating the signing, just the upload key. You upload your signed APK, and you register an app signing key. That's it. That's the whole process. You can go around freely doing your work and not being worried about it. And if you have existing applications that you want to hand over the key to Google to, then you just submit your signing key, so the one that you already have. You create an upload key. You need to update your Keystore, obviously, because you won't be signing it with the signing key anymore. And you continue the work with the upload key. Again, it's straightforward. And the only thing that you need to remember here is that this decision to hand over that key is permanent, meaning you won't be able to say, okay, I want to opt out now, and I will just be signing my application and pushing it signed to Google Play. No, it's irreversible. So that's just one thing that you have to keep in mind. So what happens in this case when somebody spills their coffee and loses their key, or it gets compromised? For instance, somebody leaves the company, it takes the data with them. Well, Google to the rescue again. You can always say that, hey, I need my key revoked, I need it reset, I need a new one, and you will get one. You just need to submit a request to Google. So, yay, one of the big issues here has been kind of thwarted, and we have an answer. Again, this might not be something that you're interested in if you have a good enough process, or you might just be brave enough. It really doesn't matter. So it's a best practice, but you're not obligated to do it, of course. So another question that I had gotten at some point in time is whether or not you should be using the same data for signing for all your modules and all your applications. Now, this is typically a business decision. For instance, if you have two applications that need to communicate and shared permissions, then you might be able to kind of say, okay, I will use the same data for each module or each application. So again, you need to value the pros and cons, whether or not it works for you or it doesn't. And the cons, obviously, you have a single point of failure, as always. So the decision is basically on you. I cannot give you that answer. You must determine for yourself. Okay, now this has kind of covered the certificate and why it matters and what should we do with them and how it works part. And now we need to look at under the hood, basically when we need kind of sensitive data and we need to store some kind of cryptographic info or generate keys, how do we do that? So Android has something that's called a Keystore system, and that system is here to safeguard your cryptographic keys from extraction. And extraction truly is the biggest risk here, meaning that once you create something, you want to be sure that it cannot be extracted from your device. So how would you usually be able to get any kind of stored data in your Android application? What would you need to do with the device? Exactly. So lovely gentleman up front said you need to root your device. When you root your device, you can get to any kind of data stored in the application. So shared prefs, external storage is already visible, so you don't need to actually have any kind of effort there. But basically the private internal storage, you can get to everything. And we need to be able to store data in a way that it cannot be extracted. So just one more question in terms of storing sensitive data. So should you store any kind of sensitive data in your application? So I created a small UML diagram that kind of leads you to the proper decision, and it basically goes like this. Is that data important? If it isn't important, then you really don't need it in your application, sensitive or not. If the data is important, then try not to keep it in your application. So try to avoid doing that in every possible way, because it's simply not worth it. So if it's that sensitive, then it might not be, the mobile application might not be the place to hold it. So we're talking about extraction prevention. What's typically done is that any kind of material is bound to some kind of, secure hardware, an element like trusted execution environment or SE, and that material that is stored there, it's never exposed outside of that hardware. So we're keeping it somewhere, boxed in, and we're not doing anything with it. It's just there. So if you need to check something, for instance, if anything is enabled for a certain key, you have the API to get information for that key and check whether or not it's, let's say, insecure hardware. Now, what are the uses for those keys that we create? Well, typically, once we define them, they're immutable, meaning you will either have to create a new one, but you won't be able to modify an existing one. And that's a security feature because it has its purpose, and basically modifying it's saying either you didn't concept it correctly to begin with, or somebody is trying to mess around with it. So it's immutable. Obviously, cryptography, and you can define that something is valid or accessible within some kind of time period. For instance, you unlock your phone and you are able to retrieve something for the next 10 or 15 seconds or something like that. It gives you kind of options to work with data. And of course, user authentication, which is very, very useful. Now, we have these utility methods available from API 23, basically that tell you whether or not something is inside a security hardware. The first one says, is inside security hardware, so that's pretty, self-explanatory. And you have this long one, which was basically, I'm sure that at least 10 people discussed how they're going to call it, and this kind of big sausage was the way to go. Is user authentication requirement enforced by secure hardware? But it gives you the information that you need, so we're going to let it slide. And what you need to decide here is basically, it's not just the Android Keystore provider, you have the keychain. You might use one, you might use the other based on your business needs. And again, that's a sole decision that you need to make. But if you go with the keychain, it's accessible, I think, from API 14, so obviously a bigger number of devices will be able to use it. It has the system-wide credentials, meaning that you use one set of credentials for all the things, and it has a system-provided UI, which we all know that, it's beautiful, it's stylish, and it's right up to the point. And just a show of hands, who here uses their password for more than 2 entities or signings or social media? Okay, one takeaway, change your passwords after this talk, but not on the public Wi-Fi, do it somewhere else. Okay, so that goes for the keychain, and if you want to use the Keystore provider, it obviously allows you to use app-specific credentials, which is good. You can create each one for a specific purpose. There's no interaction, it's under the hood, so no need for that system UI. And again, it's available from API 18, so fewer devices are able to use that. Okay, so what do we typically need to work with those keys? Well, we need to generate a pair of keys to begin with. We typically need to list the existing ones. We need to be able to sign data. So basically, we're signing some kind of data. If you're communicating something to the backend server, you might need to sign it for that server to be able to verify that everything is okay. And again, you might get something back, and you will need to verify that the signature of what you got is valid. Again, we need to check if stuff is okay. Now, the API for this is, again, straightforward. You can use Kotlin, you can use Java. Basically, both examples are available. We're just going to run through it quickly. When you need to generate any kind of key pair, first you call an instance of an algorithm of your choice. It's the elliptic curve here. And you gave it some kind of name for the key pair generator get instance. After that, you initialize a builder. And here you're able to tell this piece of code what is the purpose of your key. Now, we already said use a specific purpose for a specific task. You do not need to set all the values here because you want to granulate it. It needs to be separated properly. In this case, purpose sign and purpose verify, which is OK. And you set a digest, and you build the whole thing. Once you're done with that, you generate the key pair. Again, straightforward. There aren't many options here to change and improvise. After that, you have a generated key pair. If you need to list entries that you already have, you get that instance from the Keystore, you load the data in, and you can iterate through those aliases. Again, fairly straightforward, not much code to write, it's fairly easy to understand. If you need to sign data, and this is from what I witnessed a more common use, again, you create an object signature, you get an instance based on the algorithm that you want to use, you initiate with your private key that you retrieved. After that, you update the data that you want to sign here, and you get the signature in byte array. Again, fairly straightforward. The last action, and that's the verification of signatures. Again, you create a signature, you get the instance with the algorithm that you used, and you initiate the verification by the certificate from your entry. After that, again, update the data, and you get a nifty little boolean that says that it's verified or not. Now, what's very cool, which you can obviously use, is something called key attestation. It's a process that gives you more confidence that the keys that you are using are actually in the device's hardware-backed key store, which is what we want to begin with. But again, the downside is that only a small number of devices, I think API 24 and onward, support hardware-level key attestation, meaning that that's not available for those below that. Which is a common trait on Android. You cannot encompass everything and be able to use the newest API and newest functions. So in key attestation, you check whether or not any kind of key is stored in a hardware-backed key store. We already said API 24 and onward. And since Android Pie came, I still cannot get over the fact that they called it Pie instead of Pancake. I was really rooting for Pancake, but hey, you cannot have everything you want. They introduced something called key rotation. They introduced something called Strongbox Keymaster, or that's the hardware security module. So basically, they have revamped the whole thing by allowing more things to be done. And many, many other things, of course. But the biggest problem that we're facing in terms of what we can use and what we can utilize here is the fact that Android is still fragmented. So if you want to get everything, you cannot use the newest methods or the newest API. And your business kind of case is what will determine what you will use. You will either try to get the most users, or you will have the small number of users, but it will be super secure for now, because in a few years' time, we simply cannot know what will happen. It will definitely be shifted in some manner. So what I would like you to do, and what you can do, especially if you're communicating with third-party servers or you have your own product, I would like you to go to SSL Labs. It's a Qualys website where you can enter your domain, and it gives you the most comprehensive output of security, of the algorithms that you use, the ciphers that are used. Basically, it gives you a grade for your website. It can be A+, which is really, really high grade, or it can tell you that there's something horribly wrong. But as Android developers, you get an extra benefit there because you get a list of APIs on Android that will be able to connect to your website. For instance, if some ciphers are used, or if something is not supported, that's the way to check the whole thing. And at this point, I would like to thank you for your attention. I know that you were tired, and if you have any questions, feel free to find me after the presentation, and I'll be glad to chat with you. Thank you.